The AdaBoost algorithm works as follows. First step, initialize all the weights of the examples to wi equal 1 to n, which is when n is the number of examples. So initially, all examples have the same weight because we didn't run any machine learning algorithm yet to decide which ones are the examples that are hard to classify. Afterwards, we're going to derive m weak learners or weak classifiers. We're going to feed the classifier g of m of x to the training data using the weights wi. We calculate the error m as the weighted sum of the sum of the errors divided by the sum of the weights of all the instances. Then we compute the importance of the classifier alpha m, which is the logarithm of 1 minus the error divided by this error. The individual weight of the examples are then updated, and the update is made such that if each example that has an error on it, which means that the previous classifier in the sequence has made an error on this example, will be scaled by a factor of exponential of alpha of m, which will increase its influence or its weight. So this is a way to increase those examples on which the classifier g of m has made an error. All right, then the output of this classification is, as I said, the sign of the weighted sum of the different classifiers weighted by the importance of each of these classifiers. Let me give you a very simple example of a very weak classifier called decision stump. A decision stump is a simple two-terminal decision tree for binary classification. So the function is a function f for an example xi given a feature j and the cutoff point t, right, in the values of j. The function will be equal to +1 if the value of this feature for this individual or for this example is bigger than t, -1 otherwise. So it's a very simple decision tree in which we have here the variable xj. If xj is bigger than t, we decide that it is +1. If the variable is less or equal than t, we decide that the class is -1. So this is a very, very simplistic decision tree, one feature at a time for one cutoff point at a time. Okay, so here we have the dimensions. Suppose we, in a data set of 10 features, 2,000 examples for training and 10,000 examples for testing, we're going to compare the performance of decision stumps when they are taken individually as compared to a random classifier and as compared to a classifier that is actually boosted, a boosting of those weak decision stump classifiers. So let's compare the performance of AdaBoost to a random classifier, to a decision stump, and to a large classification tree. So as you can see in this figure, we have a plot of the test error with respect to the number of iterations in the boosting, right? So a random classifier would have a performance of 50% error rate. So and this will be something that would come in this line here. So that would be our random classifier. If we take one stump at a time, we expect this to be very poorly, but a little bit better than random. So in this case, the stumps would have a performance of 0.45 error rate, and this will make it come to this second position here. So this is our stump performance. The error rate is of 0.45. If we devise a decision tree based on the data and all the features and we develop the whole tree, we can find a performance of 24.7% of errors, and this will be our decision tree performance. And you could observe that as we do more and more iterations using a boosting of the decision stumps as weak learners, we achieve a very interesting performance and a decrease in the error rate that could go as low as 5.8% of errors after only 400 iterations. So you can see that decision stumps by themselves, when taken individually, perform poorly. A decision tree could have a performance of 24.7%, but however, it's going to be beaten by when we combine these very small weak learners together. We're going to, after several hundreds of iterations, we're going to perform to achieve a much lower error rate on the data. Okay, so one of the interesting features of using boosting with the decision stumps is that it can be seen as a feature selection algorithm, Why? Because we're going to, for each of those classifiers, remember we have, for each of the classifiers G of M, we are getting an alpha of M that tells us how important is this classifier in the final answer, right, of making the decision. So likewise here, since we are deciding on each feature at a time, so xj, we're going to, for each of those classifiers, obtain an alpha M that tells us how important is this feature in the final decision. So this is could be seen in this example of spam filtering, in which we have the words of the emails in the Y column, and we have the relative performance, or this would be the alpha of each of the classifiers based on each of these features individually. So decision stumps, AdaBoost with decision stumps can play an interesting role in defining which are the features that are most important in making the decision. Now let me give you a hint of what bagging and bootstrapping are. So first of all, bootstrapping is a resampling technique, which means sampling from the empirical distribution, and the aim is to improve the quality of the estimator or the classifiers. Bagging and boosting are both based on bootstrapping. So both use resampling to generate weak learners for classification, but with the exception that boosting is going to alter the data set by putting weights on each of the examples. The strategy is to randomly distort data by resampling and train weak learners or resample training sets. Bagging is a compact way to say bootstrap aggregation. So bagging works as follows. So for B equal to 1 to B, draw a bootstrap sample. The idea is to draw different samples from the data and build different classifiers based on these samples. And the classification then is a majority vote among the B trees or the B classifiers. So F average is 1 divided by B, the number of samples, weighted sum of the functions of B at X. Now I will give you a little hint of what our bagging and bootstrapping are. I'm leaving the details for the machine learning course. First of all, the concept of bootstrapping is about resampling. It's a resampling technique, which means sampling from the empirical distribution. The aim is to improve the quality of estimators. Bagging and boosting are both based on bootstrapping, and both use a resampling to regenerate weak learners for classification. So the strategy is to randomly distort the data by resampling and train weak learners on resample training sets. So bagging stands for bootstrap aggregation, and it works as follows. So suppose we have a sample or training data set. We're going to sample from this data several times, build the learners, and then average the results, simply average the results on all of this, on all quick classifiers obtained from the sample data. So the training is very simple. So for B equal 1 to big B, draw a bootstrap sample, B of size L from the training data, and train the classifiers, F of B, on the sample that we just draw. The classification is done again by majority vote among the B trees or the B weak classifiers, right? So such as the average, the function or the outcome would be 1 divided by B of the outcomes obtained from each of the classifiers. In general, we have observed by empirical experimentation that actually bagging works very well for trees. So if we use different samples and apply decision trees, you're going to get a set of decision trees, and having them do a majority vote on those trees will perform better than the full tree developed on all the data. Random forest is a special kind of bagging with trees that is intended to reduce the correlations between the trees. So in this case, the trees are trained and to optimize each split over all dimensions. So for random forest, we need to choose a different subset of dimensions at each split. So remember, when we were building a decision tree, each time we were to pick a feature at some point, we were considering all the features, calculating the gain, and pick the feature that actually does a better split of the data. So in the case of random forest, we're going to just pick a feature from a subset of the features, which means that we're going to reduce the dimensions from D to M and pick among the best features among this subset of dimensions. So the subset is chosen at random out of the 1 to D dimensions, and it is recommended by practice to use M is equal to square root of D at each split in the tree. So this was just a hint of what random forest and bagging can do. I would like to mention that these are really today powerful machine learning methodologies that are comparable to support vector machines, neural network, and deep learning. So think of combining your classifiers. If you think that the single classifier doesn't perform well, create an ensemble of those classifiers, and chances are you're going to get a much better decision out of those combinations. Hope this helps.